Welcome everyone to the next lecture series on the unit Electromagnetics. So I have referred to these different textbooks on engineering physics by Pearson Publications. It's a DSU edition. Then we have the Eastern Publications and the Wiley Publications of Engineering Physics. Then the University Physics of Pearson Publications. Fundamentals of Physics by Halliday and Resnick, very famous book on physics. And also to the MIT open courseware lecture notes and presentations available online at the MIT webpage. So that's the outline of this lecture series on electromagnetics. So we start with some concepts of gradient, divergence and curl of a vector field. Then we move on to electric field and superposition of charges. Then comes the relation between electrostatic potential and electric field. We then come to the electric field, applying the electric field using Gauss law, obtaining the Gauss law, that is which is with the divergence of electric field, and then apply it to get the Poisson and Laplace equations. Next comes the divergence of magnetic field, that's again a Gauss law for magnetostatics. After that we have the Faraday's law for electromagnetic induction, which represents the curl of electric field. Then we have the Biot-Savart law, the concept of vector potential, curl of the magnetic field, which is given by the Ampere's law. Then we introduce the concept of displacement current and hence obtain the continuity equation. We apply the concept of displacement current and then get the modified Ampere's law, and at the end we bring in the Maxwell's equation and try to obtain an expression for the speed of light using Maxwell's equations. And we will see some numerical problems and solutions in the last lecture. So starting with some useful information or interpretation of gradient, divergence and curl. This is very important when you need to study electromagnetics or in future the electromagnetic field theory or any variations of fluid dynamics like that. So we start with gradient. So we have considered a ball here, and let's just assume that at any point on the ball there is a vector acting perpendicular to that ball. So all these lines which look like thorns are actually representing some vectors acting at that particular point on the ball. So this vector is actually representing what is called as a gradient. So if I have any scalar function, say a capital phi of xyz because it is three-dimensional I have considered. So the gradient at any point on this function phi of xyz will be a vector which is perpendicular to the surface of this function phi and is also passing through a particular point. So suppose this is the surface and we have the surface, there is a particular function phi acting on this surface, let it be temperature, then the gradient of that function phi will be a vector perpendicular to this surface of that function, and it will be passing through a particular point. So a few examples are variation of temperature in a room, and so we call it as a temperature gradient. So another simplest example is whenever an airplane is doing takeoff, so we can see that the height increases as it is moving away, right? And when it is flying, it is at a different height, and also while it is coming down, while it is landing, it is taking different heights. So the altitude varies with position. That variation is represented as a gradient. Now let's see how to do this mathematically. So we consider the same function phi of xyz. Then the gradient of phi is given by del phi. Del is the operator, mathematical operator. Del phi will be unit vector I dou phi by dou x plus unit vector j dou phi by dou y plus unit vector k dou phi by dou z. Now let's see some important properties of gradient. So if there are two functions f and g, then gradient of f plus g will be gradient of f plus gradient of g. If it is gradient of f minus g, then it's very simpler, it's just similar to the previous. We have gradient of f minus gradient of g. If we get gradient of a function as 0, that means that function is a constant function. Now suppose if f and g are scalar functions, then gradient of the product of f and g, f into g, is f into the gradient of g plus g into the gradient of f. Now suppose we have a constant c, then the gradient of the constant into the function f is the constant c into the gradient of the function. So all these properties of gradient will be useful as we go ahead with the unit of electromagnetics. Next we have the concept of divergence. So divergence, like, it's better to understand whenever you consider a fluid flow. So we have considered here a pipe, a long pipe, and which is actually made up of many small pipes, and there is some water flowing through the pipe. So whenever there is water flowing through this longer pipe, we can see that more water can be added through the smaller pipes also. So the total flow rate will increase as the water flows through the different pipes, even the smaller ones. Suppose if there is a leakage in the pipe, then there will be decrease in the flow rate. So such change in the flow rate, either it is a decreasing or it is an increase, it can be represented by the divergence. So we can just show it here. So this is when the flow rate is constant, initial and final flow rate is constant of the fluid, then the divergence is 0. When we have the initial flow rate lesser than the final flow rate, then the divergence is positive. If the initial flow rate is more than the final, then we get the divergence as negative. Now once again, so let's see how to represent divergence mathematically. So divergence acts on a vector function. So we have considered a vector function f at position x, y, z, once again in 3 dimension. So the divergence of this vector function f is given as del dot f, that is the operator del, that's represented by unit vector I dou by dou x plus j dou by dou y plus k dou by dou z dot the vector f. So that turns out to be unit vector I dot dou f by dou x plus j dot dou f by dou y plus k dot dou f by dou z. So the resultant will be a scalar. Resultant is a scalar quantity. So we need to see that divergence is an operator. So if we do del dot f, then it is not the same as f dot del. Now suppose if the function f is a constant vector, then divergence of that vector function f will be 0. And if we consider a constant c, then divergence of the constant c into the vector function f will be c, that's a constant, into the divergence of the function. Next, let's look into some examples of curls. So suppose when we pour water in a cup, we can see that as it reaches to the top, it will be rotating and then only settling up. The same way, when you have a kitchen sink and the water is flowing through the sink, through the drain, you can see that it will rotate before it goes out. So this rotation is actually what is represented as a curl. So curl is actually a measure of how a vector field will rotate or circulate about a particular given point. If the rotation is counterclockwise, then we say that the curl is positive. If it is a clockwise rotation, then the curl will be negative. So some examples is rotation of a rigid body, that is a top. If you consider a simple top, when you are rotating, that is actually resulting into a curl. Whereas we have hurricane and cyclone. So I just given an example of a hurricane over here. So you can see that it actually rotates about a central point. Okay, now mathematically, let's see how to represent it. So we again consider a vector function f of xyz, again in 3 dimension. Then the curl of the function is given as del cross f. So del, as we know, is I dou by dou x plus j dou by dou y plus k dou by dou z. Then cross f, the function f. So it can be written as I cross dou f by dou x plus j cross dou f by dou y plus k cross dou f by dou z. Now suppose if we represent this vector function f as f1 into unit vector I, f2 into unit vector j and f3 into unit vector k, then it's very easy to find the curl of this function by taking determinant. So sorry for that. So what we need to do is we consider for the determinant first the unit vectors ijk, then the coefficients of the operator del, that is dou by dou x, dou by dou y and dou by dou z, and then the coefficients of the function f, that is f1, f2, f3. Just take the determinant, you get the result. Now the resultant will be always a vector quantity. Resultant of a curl of a vector will always be a vector quantity. And once again, the curl operator is not commutative. So that means if you do del cross f, then it's not the same as f cross del. Now if you have a function f, vector function f as constant, then its curl will be 0. Now suppose f is a vector function and c is a constant, scalar constant, then the curl of constant c into f is c, that's a constant, into curl of f. So let's see some important vector identities which we will need. So we have del dot scalar function phi into vector function f, that is basically we are taking a divergence of a product of scalar and vector functions. So we get gradient of phi dot f plus phi into divergence of f. Next we have curl of the same product, scalar function and vector function. So we get gradient of phi, its curl with the vector function f plus phi into the curl of the vector function f. Now suppose it is divergence of a curl, let's see how it is. So we have two functions, two vector functions f and g. So it is del dot f cross g is given as g dot del cross f minus f dot del cross g. Now a very simple identity to remember, a few of them. So divergence of a gradient of a function will be del square of the function. So we just note that del square is dou square by dou x square, where because del was dou by dou x. Now curl of a gradient, that is del cross of del phi, is 0, and divergence of a curl of a function, vector function f, will be 0. What happens to curl of curl? So we take a vector function f and try to find del cross f, that is given by gradient of divergence f minus del square f. So that is del of del dot f minus del square f. Very important relation which we will be using later. And next, suppose we have a constant c and we take the product of the constant with the vector function f and then find its divergence. So then del dot c into f is c into divergence f plus gradient of c dot f. Next we need to know about the Gauss divergence theorem. So we are going to consider a surface denoted by S as a smooth surface, and it is being bounded by a volume capital V. Now suppose we have a continuous function capital F xyz, a vector function, and which also has partial derivatives in this particular volume. Then we can write volume integral divergence of f, that is del dot f into dv, is equivalent to surface integral of the vector f dot a unit vector n into the elemental area ds. So here we have unit vector n is actually a vector drawn normal outward to the surface. So, f dot n will be the normal component of the vector f. So we can define the Gauss divergence theorem as the surface integral of the normal component of a vector f taken over a closed surface is equal to the integral of volume integral of the divergence of f taken over the volume enclosed by the surface. So very important theorem which we will be making use of. Next we have the Stokes theorem. So once again we consider a surface S, and now this surface is bounded by a smooth curve, a closed curve denoted by the letter C. And again we consider a vector function, a continuous vector function having first partial derivatives. Then it's given by f of xyz, capital F of xyz. Then we can write a line integral of C, integral over the closed curve C, f vector f dot small line element dr is equal to surface integral curl of f dot the unit vector acting on the surface in outward direction into the elemental area ds. So this is all about some introduction, basic introduction to the concepts of gradient, divergence and curl, and we have seen how to represent them mathematically and some important vector identities and two important theorems, that's a Gauss divergence theorem and Stokes theorem. In the next lecture we will start with the concepts of electromagnetics, and we will be applying these rules of vectors, gradient, divergence and curl as we understand electromagnetics. Thank you.